So let's set you up to do some predictions about reactions. And what I mean by this, for right here, is that we're going to predict which way a reaction will proceed to achieve equilibrium. So this means if we start not at equilibrium, which way is this reaction going to go? So whichever direction it's moving, right? It's just trying to get to equilibrium. That's our goal. So, let's look at an example because I think some of these you could do intuitively, but we run into an issue um, in the majority of cases that we're going to see. So the reaction is H2 plus I2 in equilibrium with 2HI. We're going to do this for three sets of conditions. So the first set of conditions is if my H2 is 2 molar, my I2 is 2 molar, and my HI is 0. Keeping in mind that KEQ is a numerical value, think about how you calculate KEQ. The way that this reaction would move is to the right because it starts with a zero product. If in our equilibrium constant expression, the product concentration was actually 0, my KEQ would be 0, and you will not see a KEQ of 0. So you have to have something. Even if it's one molecule, the tiniest concentration, the product has to exist, the reactant has to exist in order for it to be at equilibrium. So no product has to move right. Second set of conditions, if my H2 is 0, my I2 is 0, and my HI is 5, I don't have any reactants, right? If this were my equilibrium values, my equilibrium constant would be undefined. So, which will not happen. So this reaction has to move to the left. It has to form reactants. But what about if H2 is 4 molar, I2 is 4 molar, and HI is 3 molar? So, I could calculate products over reactants, but that's not the equilibrium constant because I'm not at equilibrium. So I have no idea. I have no reference to tell me, is this balance appropriate? Is this balance close to what it wants to be at equilibrium? Right? I have no outer context, nothing to compare it to. So that's what we're going to learn how to calculate. So if you want to know which way a reaction is going to move, first you need to know where you're trying to end up. But then you also need to know where you are. So in our equations, right, where you end up, that's the equilibrium constant. That at equilibrium is where we are trying to be. KEQ is the numerical value that tells us the balance at equilibrium. The where am I now? We call this the reaction quotient. And I'm going to go in how to get the reaction quotient. This Q reaction quotient, it's going to come back up in multiple modules, so don't forget about Q. It tells you where you are now. So the reason that this is important, I'll try to make this like on a big scale. So imagine I am trying to travel to Chicago, right? Chicago is the where I want to end up. That's the equilibrium constant. Now, the way you tell me to get to Chicago is going to depend on where I am. If I'm in Wisconsin, you need to tell me to go south. If I'm in Florida, you need to tell me to go north. And also a little bit to the west and in Wisconsin, I guess it depends on where you are in the state. But if I am in Maine, you need to tell me to go west and a little bit south. Right, the place that I am at determines the way I need to go to get to my destination. So that's why we calculate the reaction quotient, is to figure out where my reaction is so I know which way to go to get to equilibrium. So the good news is that you calculate the reaction quotient the same way you would calculate an equilibrium constant. It just does not require the reaction to be at equilibrium. So in my generic reaction, it's still products raised to their powers divided by reactants raised to their powers. And if we're talking about pressures, it's the same thing. Pressure of products raised to their coefficient powers, etc. So what we do to figure out which way to go, we calculate Q and then we compare it to K. Now, there are a bunch of different ways that you can imagine this happening. A lot of books will give you references of like Q divided by K being less than, greater than, or equal to 1. If you want to talk about what that looks like to calculate, I'm always happy to help you. I like to do it this way. Again, not the only way to do it. So if this doesn't work for you, we'll find one that does. Compare Q to K, write the value for Q on the left, write the value for K on the right. If Q is equal to K, you are at equilibrium. They have the same form. When the values are from a reaction at equilibrium, it is the equilibrium constant. Q equals K, you're there. Q less than K. So mathematically, Q less than K means numerator divided by denominator is smaller than it's supposed to be. So my numerator needs to be bigger relative to my denominator. That means making more product. So my reaction will move to the right if Q is less than K. Now, the way that I remember it, right, if you think back to whichever part of elementary school they taught you greater than and less than signs, right? Q less than K, if you imagine that this less than sign is a little alligator mouth, and I've drawn some little chompy teeth in here, right? It's chomping toward the K, which is on the right. So little chompy mouth pointed to the right, my reaction goes to the right. Q greater than K, now numerically, mathematically, Q greater than K means numerator is too big compared to denominator. I have too much product. My reaction is going to go to the left to get rid of some of it. Or Q greater than K, my greater than sign, the little chompy mouth that has the teeth in it, is pointed at the left. So my reaction would go to the left.